Welcome back everyone. In the last couple of videos we've been talking about distance and displacement and how we can find those geometrically as the area under the curve of a function. And in those videos we talked about how we can estimate that area because we don't have a way to find the exact area under a curve if it's an unfamiliar shape. And in this video we're going to leave the context of distance and displacement behind and start talking about how we can actually find the exact area under a curve. And that journey towards an exact answer starts by considering how we can possibly improve our previous approximations. Take this function here for example. We are using 4 rectangles with a left endpoint approximation to approximate the area under the curve. And we can see that it's not perfect because there are still some gaps between the rectangles and the curve of the function. And the reason it's not that good is because the subintervals are just too wide and they can't capture how the function is increasing over time. And so we can improve this by reducing the length of each of these subintervals. And in doing that, we're going to have to use more rectangles as well. And by having the length of each of these subintervals, I have to use 2 times as many rectangles. And that's why I have 8 rectangles here instead of 4. And we can see that this is already a better approximation than before because the gaps between the rectangles and the curve are smaller than before. But it's still clearly not perfect. So let's try to improve this estimation even further by using 16 rectangles instead of just 8. And we can see that it improves it even further. The gaps have become smaller and smaller. And let's improve this one more time by using 100 rectangles instead of just 16. And by this point you can hardly even see the gaps between the rectangles and the curve. And this is a significantly better approximation than when we used fewer rectangles. And as you might imagine, as I use more and more rectangles, I will get a better and better approximation. And what I'm trying to get to here is that if I took the number of rectangles and let that number approach infinity, that would give me the exact area under this curve, because that approximation would continue to improve, become better and better as I added more and more rectangles. And we can let that number approach infinity by using limits. Now before we get ahead of ourselves, we need to take a moment to stop and try and generalize this process of adding up the area of rectangles to approximate the area under the curve. Now going back to when I had just 4 rectangles, let's label a couple things on this picture that we're going to use for notation later on. And let's label each of the endpoints of the subintervals. Let's call the first endpoint x0, the next endpoint x1, and so on from there. And let's call the width of each of these rectangles delta x. And notice that delta x is the same for each rectangle. So let's use this notation to figure out what the area of each of these rectangles is. So this first rectangle on the left is going to have a width of delta x and a height of f of x0. And the reason that's the height is because we are using the left endpoint approximation, and the left endpoint is x0, and so the height of this rectangle is the height of this function when evaluated at x0. That height there is f of x0. And so the area of this first rectangle is f of x0 multiplied by delta x. Now moving on to the next rectangle, it's still going to have the same width of delta x, but now the height is the height of the function evaluated at x1, and so the area of this rectangle is f of x1 multiplied by delta x, and so on and so forth. And the reason we're doing this is to really say a general statement about how we're going to be able to find the area under any function. We need to start by generalizing our notation. And now that we have that picture in our head, let's try to write it all down with words. So let's say that we have a continuous function on some closed interval from a to b. And we're going to divide that interval into n subintervals. You can think of n as being the number of rectangles that we're using for our approximation. And we need to know the width of each of these rectangles and the height of each of these rectangles. And the width of each of these subintervals is delta x, and delta x is b minus a divided by n. Now where did I get that from? Well, b minus a is the length of the entire closed interval from a to b, and we're dividing by n because there are n subintervals. So we're taking the length of the entire interval and dividing by the number of subintervals. And let's label the endpoints of this subinterval. And we're going to use the same notation from the picture, where the first endpoint is x0, the next one is x1, the next one is x2, and you go all the way up to xn. And we're generalizing this to let n be the number of rectangles, and that's why the last endpoint has to be xn. In the picture earlier, there were 4 rectangles, and that's why the last endpoint was x4. But now that we have the endpoints of the subintervals and the width of each subinterval, we have enough information to find the area of each rectangle. And again, we're using the left endpoint approximation. And so if our first subinterval is from x0 to x1, we're using x0 as our endpoint for the left endpoint approximation. And so the height of that first rectangle is f of x of 0, because the height is the value of the function evaluated at x0. And the width of each subinterval is delta x, and so the area of the first rectangle is f of x0 multiplied by delta x. And we'll do the same thing for the next one. The second subinterval is from x1 to x2, and the left endpoint is x1, and so the height of this second rectangle is f of x1, because the height of the rectangle is the height of the function evaluated at x1. And the width is still delta x, and we multiply those two values together to get the area of the second rectangle. And you do that for all of the other rectangles, and the very last subinterval is from xn minus 1 to xn. And out of those two, which one's on the left? Well, it's xn minus 1, and so the height of the last rectangle is f of x sub n minus 1. And again, you take that multiplied by delta x, and that is the area of the final rectangle. And notice that all of these terms have a delta x in common, so you could factor out the delta x if you wanted to. So as long as you have a continuous function on a closed interval from a to b, you can use this formula here with any number of rectangles that you want to get the left endpoint approximation. Now there is nothing special about the left endpoints. I could have done the same exact process but with the right endpoints instead to get the right endpoint approximation. Now the computation for delta x is still the same, and the endpoints are still the same given the same number of n subintervals. But to get the height of each of these rectangles, you use the endpoint on the right side of the subinterval as opposed to the left side. So if the first subinterval is from x0 to x1, we're going to use f of x1 to be the height of the first rectangle, and we'll do the same thing for the next one. And the second subinterval is from x1 to x2, and the right one there is x2. And so the height of the second rectangle is f of x2, because that's the height of the function on the right side of this subinterval. And we multiply that by delta x, and so on and so forth. Now our very last subinterval is from xn minus 1 to xn, and the one on the right is xn. So the very last rectangle would have a height of f of xn times delta x. So this is very similar to the left endpoint approximation, just the endpoints that we're using are slightly different. But once again, with any continuous function on a closed interval from a to b, with any number of rectangles that you want, this formula here will give you the right endpoint approximation. And I know this notation is kind of tough to digest the first time you see it, so before we get to the real punchline of this video, let's go through one example of using one of those formulas for a particular function on a closed interval. And let's estimate the area under the graph of x squared on the closed interval from 0 to 2 with 4 rectangles using a left endpoint approximation. And since we're using 4 rectangles, that's a giveaway that n is equal to 4. And so if I use the formula from earlier, the left endpoint approximation is going to be delta x times f of x0 plus f of x1 plus f of x2 plus f of x3. And all I did here was plug in 4 for n, so I know where to stop this summation. And now we just got to figure out what delta x is and what the endpoints of the subintervals are, and then plug those into the function. And delta x is b minus a divided by n, and a and b are the endpoints of the interval, and so b is 2 and a is 0, and so the numerator is 2 minus 0, and then we're dividing by 4 because we are using 4 rectangles. And you simplify that and you get 1/2. And so the width of each of these rectangles is going to be 1/2. And now for the endpoints of the subintervals, keep in mind that the entire interval starts at 0, and so our first endpoint, which is x0, is going to be 0. And to get the other endpoints from there, keep in mind that the length of each subinterval is 1/2, and so the distance between these endpoints is also going to be 1/2. And so if the first endpoint is 0, the next one will be 1/2, and then 1, and then 3/2, and then 2. And from here, we just plug everything in where we should. And the answer is going to be 1/2 times f of 0 plus f of 1/2 plus f of 1 plus f of 3/2. And notice I didn't actually use the endpoint x4 because that's only the right endpoint of the last rectangle, and we're using a left endpoint approximation. But it's not really an answer until we evaluate the function at each of those points. And since the function is x squared, f of 0 is 0 squared, and then f of 1/2 is 1/2 squared, f of 1 is 1 squared, and f of 3/2 is 3/2 squared. And the reason that we're squaring these is because the function is x squared. If it's a different function and you square the numbers anyway, then your answer is going to be wrong. You should be doing whatever the function is defined to do. And if you simplify all of that, you'll get an answer of 1.75. And this is the left endpoint approximation of the area under the graph of x squared on the interval from 0 to 2 with 4 rectangles. And if you were doing a right endpoint approximation, the overall process would be the exact same, just your formula for the approximation would be slightly different. But the delta x would still be the same, the endpoints would still be the same, just the endpoints that you actually use would be slightly different. And now that we have an idea of what the notation means, let's try to bring it back to the main idea for this video. And I want to repeat that this left endpoint approximation is an estimate of the area under the graph of the function. And it's clearly not an exact answer for the area under the graph. And from the beginning of the video, we talked about how we can improve our estimation by using more and more rectangles. And so if we take that number n, which is the number of rectangles, and let it approach infinity, we will get the exact area under the graph of the function. And this formula here is known as a Riemann sum. And if you were to compute this, this would get you the exact area that you're looking for. And it's just the thing from above, but the limit as n approaches infinity is out in front. Now writing all that out every time would be cumbersome, and so we have a bit more notation to introduce to compactify that idea. And let's say that we have a continuous function f on a closed interval from a to b, then the definite integral of f from a to b is represented by this squiggly line with an a at the bottom and a b at the top of f of x multiplied by dx. And this thing here, this notation, is equal to the formula from the previous slide for the exact area under the graph of f of x on the interval from a to b. But written as this, we call it the definite integral. And a little bit more vocabulary, the function f is called the integrand, and the endpoints a and b are called the limits of integration. And the dx there represents the delta x on the other side of the equality. So this still captures the idea of adding up the area of all these rectangles, where f of x is the height of each rectangle and dx is the width of the rectangle. Now actually computing this thing is easier said than done, and over the next couple of videos we're going to talk about just that, how we can compute this thing. But for now, keep in mind that this definite integral represents the exact area under the graph of f of x on the interval from a to b.